Jai Hind. Today our topic of discussion is uninformed search. When we solve a problem by searching technique, so we search from some particular state and then we go on exploring the state. So we are having different strategies when we talk about the solution of a problem with help of searching. So in this particular lecture, we will talk about search strategies, what are the different type of search strategies that we can apply, and then we will focus on one of the types, that is uninformed. Among the uninformed search techniques, we'll talk about breadth first, depth limited, IDS and bidirectional search techniques. My reference that I'm referring here is Artificial Intelligence, a Modern Approach by Stuart Russell and Norwich. So let us discuss, let us start with our topic of uninformed search. So I just told that a problem that we are solving with help of searching. Okay, so when we say we are searching, so definitely we'll start search from somewhere. Okay, when we are starting the search from somewhere, it means we are having an initial state. Let me call this as the initial state. So from this initial state, multiple next states may be possible. Now when we are talking about those multiple next state, a search strategy is one that gives us the order of node expansion. We will be picking the next node to explore, to search the solution. Okay, so a search strategy is the selection of that particular next node. In what order the nodes will be expanded. Let me say I am having 3 nodes A, B, C, and I am having a start state. Now if I am having these next possibilities, that is A, B and C, among these A should be explored first or B should be explored first or C, that depends on the way we are picking the order. So that is a search strategy. When we are having different existing search strategies, so how do we evaluate those strategies? Okay, because finally what we are going to use, that depends on different parameters. So firstly we'll talk about, to start with the search strategies, we will talk about the parameters on which we will evaluate these strategies. So first one is completeness. Whenever I apply some search strategy, so first point I need to know is it able to find the solution? Okay, because there may be some problem for which solution doesn't exist, but if a solution exists, then our search strategy should be able to reach to the solution. Okay, so that is the completeness property. Whatever strategies we are using, whatever algorithm we are using, is that able to find the solution when there is one? It means solution exists. So the search strategy is able to find out that solution or not. That depends on the algorithm is complete or not. That is the completeness property. Now whenever an algorithm will find a solution, it will take some time and take memory, consume memory while doing the searching. So those are called time complexity and space complexity. And whenever we are finding a solution, it may be the case that there exists multiple solutions for the same problem. For example, if I have to go from one source to destination, there may be more than one path to reach from source to destination. So we should know that, we should evaluate that the algorithm is able to find the optimal solution or not. Many solutions exist, but among those there may be some optimal solution, so which is desirable. What is desirable? The best, in which we need to pay low cost. Okay, so the algorithm is optimal or not, it means is it able to find the optimal solution or not, that we will check. Okay, so for doing all these evaluation, we are assuming here three notations B, D and M as per the text reference that we talked about by artificial intelligence, a modern approach. I am taking the same parameters. So what is B? Whenever I am having a node, it can have one successor node, 2, 3, 4. Okay, so what we are saying that whenever a node, maximum possible successor nodes are B. Node can have maximum B successors. Second is D. What we are referring to D? D is the depth of shallowest goal node. It means, let me say multiple nodes, multiple goals are there. So let me say one goal is at this depth and one more goal is somewhere here. So the nearest goal is this. So what is the distance of nearest goal? That we are taking as the depth. Okay, in this goal 1, this is goal 2. So D we are taking as nearest goal node, shallowest, which is at the minimum depth. And M is the maximum length of any path. If we say we are going from here to here, here to here, then to next, to what max level we are going, that we are calling M here. So we will use these three values, three variables B, D and M to represent maximum number of successor, the depth of nearest goal node and the maximum path length. So let us start with the concept. Uninformed search technique. What is uninformed search? Uninformed search means we are having only the problem. The problem definition is given and no other information with which we can get some guess is given. Nothing is available more than the problem definition. That is uninformed search. It is also called blind search. Blind search means we are blindly searching, we are not having any direction, where should we go. And if some information is given, then we call it informed search. What is informed search? If it knows that one goal state is more promising than the other one, it means some information is given which is telling us that if this state will be taken, it will be better than the other one. So there is some information, that is informed search, which is also called heuristic, because the information is given in some form that generally we call heuristic. So we also call it heuristic search. Today's topic is blind search or uninformed search. So now we'll talk about different uninformed search technique, different blind search technique in which only problem definition is given. So we'll talk about here breadth first search, depth first search, depth limited, iterative deepening and bidirectional search. So let us consider one by one. First is our breadth first search. So what is breadth first search? Breadth first search technique is the one in which we take the searching, we do the searching breadth wise. It means level by level. Okay, so what we do in BFS, breadth first search, we firstly expand the root node. Root node is expanded. What are the neighbors of root node here? B and C. So when we will expand this, then its successor. What are those successors? B and C. Okay, firstly A will be explored, then B, then C, and then their successors. What are their successors? What are B's successors? D, E, F and G. So let me consider a particular node as goal node. Let me call C is the goal node. Let me call it goal. So what will happen in this? We will firstly expand the root node. So we'll go to root node. What is root node? A. So is it goal? The goal test will fail. So we will expand it. When we will expand it, its neighbors will be considered, its successors will be considered. What are the successors? Firstly B, then C. Okay, B and C. So first successor is B. So now B will be checked. Is it goal node? No, it's not goal node. So now we'll check the second successor. What is the second successor? C. Okay, is it goal node? Yes. So we got the goal node. Firstly, we'll check the root, then its neighbors. Now in this particular case, we found the solution in its successor. But if we don't find solution, then we will check their successors and so on. Okay, so how it is implemented? Using first in first out queue. So queue data structure is used to implement breadth first search. The shallow nodes are expanded before the deeper nodes. These are when we are starting with root A, the shallow nodes are B and C and deeper nodes are D, E, F, G. In this, firstly the shallower nodes will be explored, will be expanded, processed, and then the deeper nodes. So in this way breadth first search is taken. Let me call second goal, another goal, not C but F. Let me call goal is F. So what will happen? We'll check root node, it will fail the goal node test. Then neighbors of A, B and C, both fails. When we checked B, now B's neighbors are D and E, both failed. Okay, so what will be order of checking? A, B, C, D, E, F. So we will get the goal node test true here at 6th position. So this way we will do. So what we are doing? We are doing level wise. This is our breadth first search. Now let us talk about the evaluation. We talked on previous slide of search strategies that we should know when we are applying a strategy, is it complete? What is the time complexity? What is the space complexity? And is it optimal or not? Okay. So what we are doing here, breadth first search. Is it complete? A search strategy is complete if it is able to reach to each and every node to check, do the goal test. Okay. So what we have taken B as the number of child nodes, that is the successors. So if successors are finite, okay, then definitely it will be complete. So we say it is complete because it will check each level. It will start from root node, then it will check its neighbors, then neighbors, neighbors, successors, successors, and so on. So it is not missing anything. At every node it is checking all the values, all the nodes, and doing the goal test. Okay, so it is complete. What is the time complexity? How many nodes it is working out? So it will check the first one, it will check its neighbors, okay, then neighbors, neighbors, and so on. Okay, so if we say A can have maximum B neighbors, it means A is 1, its neighbors are B, okay, then every neighbor has B neighbors, B successors. So for every, it is having B square. Now these B square nodes will have B successor again, so B cube. So first level will have one node, then B node, then B square node, then next level B cube node. Okay, so all these will be worked out. Till which point we will work out? We will go till we get the goal, and goal is at D. We said that the shallowest goal node is present at depth D. It means we will go on doing this till depth D. What else we have added to it? This is for worst case. When we are having goal at the dth at D distance, D depth, then actually at D depth we are having B to the power D nodes. In worst case, what will happen? We'll check and all the nodes, and at last node we will get the goal test true. It means when we are talking about all the last level nodes, all the nodes will get expanded before we reach to the goal node. Only that goal node will not be expanded. That's why we are saying that in next level also maximum nodes have been expanded, have been generated, only the successors of this goal node are not generated because it passes the goal test. Okay, so what we will get here? The time complexity order of B to the power D plus 1. Okay, and because level wise we are searching all, so all these nodes are to be kept in memory. So the space complexity is also order of B to the power D plus 1. This is also a disadvantage of breadth first search, that we need to keep every node in memory while we are doing the searching. We are searching for the solution. So that is the problem here. Okay, and is it optimal? Yes, the breadth first search is optimal, because if there are given two nodes, two goal nodes, and D is the depth of shallowest node, then it will reach to that node which is at the shallowest depth, that is D, because it is checking level wise. If one goal node is there, it will reach to C first. If another goal node is here, it will not go there. It will firstly check A, then all the neighbors of A, and it will find the solution at C. So it will not go for E. The nearest goal will be worked out in breadth first search. So it is optimal. So this is our breadth first search technique. Now, second one is depth first. In depth first search, again it's a blind search. We do not know where to go. So what we do, we expand deepest unexpanded node. Deepest means we'll try to go in depth as much as possible. Okay, so when we are going in depth, it means if I start with A, I'll take a neighbor and I find the goal test false, then I'll definitely go to successor. Successor is B, that is at one depth. Then rather than going level wise, we will go depth wise. Depth wise means in this direction. A to B, B to D, D to H, as much as possible. Okay, so what depth first search does, it expand deepest expanded node, and it is implemented with a stack which we call last in first out queue. So we put successors at front, and that we worked out first. Okay, so what we will do here, we will start with A. It fails the goal test. Let me say again goal is C. Let me call it the goal, and I am searching for the solution. That is my goal, which is C here. So we will start from A. Now what we will do, we will make a LIFO queue, last in first out. Okay, so what we will do, we'll start from here. A, it is having two neighbors. two successors B and C is the goal. Now from A will go to B, the first successor, that also fails the goal test, so it will be expanded. So when it will be expanded, it will go to D, that also fails the goal test, then it will come to H. So what will be order? 1, 2, 3, 4. Now 4 of H also fails the goal test, so it will check I. Then this. So total branch has been explored in deepest way, deepest in depth wise as much as possible. Now because we didn't get solution here, now it will go to this, where it will go to this. Now goal will be found. Okay, so the deepest path has been explored, and then we reach to the goal. Goal is C. So the searching is done in depth. So how actually it is implemented? It is implemented with help of our stack, because whatever we took at last, that will be explored first. That is the way we expand the deepest unexpanded node. Okay, this is depth first search. Now let us discuss important point here, that is it complete? When we talk about depth first, now generally we cannot say that depth is not infinite, that is depth is finite, that restriction we directly cannot say. So we say it is not complete, because it may be the case that solution was C, which was an other edge. We went to B, B to D, and so on. In depth we are going on, while the solution is present on other branch, and we go on infinite deeper length, and we are not able to reach to the C side, that is the other branch. Okay, and if it is finite space, it means M is finite. Okay, then the DFS is called complete. It means if depth is defined, okay, then it will be complete, otherwise it is incomplete. So in general we say that DFS is not complete. Now important part is time complexity. Time complexity. What is the time complexity? When we go depth wise, okay, so we explore level 1, then level 2, then level 3, and what is the maximum depth it can have? That is M. So maximum time it will consume is order of B to the power M. B order of B, while it was D plus 1, order of B to the power D plus 1 in depth first search. So here we are, it is taking more time, and it becomes a problem when the depth is much larger than the depth of the maximum possible depth is much larger than the depth of the shallowest nearest solution. Okay, and it works very well when the solutions are very dense. It means these are very near. Many solutions exist and these are very near. So then it becomes very fast than breadth first search in that type of situation. So according to time complexity, it is not better than DFS. DFS is better because that is taking only the time order of B to the power D plus 1, where D is the depth of the nearest goal node, while it will go to maximum possible depth. So it is order of B to the power M. But when we talk about space complexity, what we do in BFS, if this is one node, its neighbors, then neighbors. So what we talked about, that first level is having only one, then next can have B nodes, because B successors are possible. Next will have B square, B cube and so on, and all need to be kept in memory. That's why we say that it needs this much memory. But when we talk about depth first search, what it does, it take the first node, expand it, so we get B nodes. Now among these only one will be checked in depth. When we will go to next level, only the successors of that particular selected nodes are there that have been generated. So here again we will have B nodes only. Then if we say this is explored in depth, so what does it mean? It means only this particular is having further B nodes. So what we are having at this depth 2, at this depth 4, at this depth 6. So what is the maximum depth? M. Okay, so we are having linear space requirement. So in space it is far better than depth first search. And what about optimal? It doesn't give us optimal solution, because if this was optimal solution, let me say goal 1, and this is not optimal solution, let me say goal 2, so it will reach to goal 2 first, because it is expanding in this particular direction. After expanding the total depth on one branch, then it will jump to the second side, and the second side we are having the nearest goal node. It is finding the optimal solution. So what we saw on this particular slide, that it is not complete, it is not optimal, but it is very much better in space complexity in comparison to BFS. So from here we will carry that we need something which is having time complexity of breadth first and space complexity of depth first. So because depth first is having the problem of infinite depth searching, okay, so what we can do, we can have another option, that is depth limited search. Depth limited search is used when the trees are unbounded. It means there is no depth limit. It is not M, it could be anything, it may be infinite. Okay, so what we do, we define a depth limit L. Depth first search with depth limit L is called depth limited search. Okay, what we do, we search only up to depth L. We assume that nodes at depth L will have no successors. We'll just explore till that. Okay. Now, what is major issue here? It solve the problem because it is depth first based search. So it is very good at space complexity. But what happens? It becomes a challenge to decide L, because if we will take, we do not know where the node is, because if we know node, then what is need of searching? So we are searching for the goal node, and if we take the depth limit less than D, then it will not be able to search the goal. It will become incomplete. And if we will take it greater than D, that is the length, the depth of the nearest node, then it may explore some node which is goal but at larger depth. Okay, in that case it becomes non-optimal. When L is less than D, it may result in incomplete, that changes the completeness property, and if we take larger, then it may give us non-optimal solution. So the challenge is how to decide L, the depth limit. Why? Because we want depth first type of space complexity. Okay, so that's why we generally go for IDS, iterative deepening search. It is able to find the best depth limit. It gradually increases the limit until a goal is found. Okay, The purpose is we want benefit of BFS as well as DFS. It means we want to have a lesser space requirement and lesser time, and we want the optimal solution also. So it combines benefits of BFS and DFS both, but because we increase the limit gradually, so what happens, few states are generated multiple times. So that is the drawback, but that can be ignored, because when we overall see, then the number of multiple generated states are comparatively less if we talk about the depth explored in case of DFS. So how does it work? Initially we take limit 0. So limit 0, it means we are only checking the root node. So limit 0 means only root we are taking. So we will check only the root node. Let me say it failed. Then we will increase the limit. Now limit is 1. So now what happened? A and its successors. What we are having now? A and its successor. Now we are taking depth, but we will apply BFS. Okay. So now we will check A, then its successor B, then successor C. We are taking depth to use the concept of DFS as well as BFS. Okay. Now L is taken. So what we did? We took only one depth, and now we applied the searching. We checked A, then B, then C. Now we increase the limit to what we want. We want the nearest node, shallowest node like BFS. Okay. But actually what we want? We want the space complexity like DFS, because that takes the linear space. That takes linear space. Okay. So by taking limit 1 on last slide, what we tried to go level wise. Okay, but we didn't. So what we actually applied by taking just one depth, we actually applied something similar to BFS. Okay, but now we didn't find solution here, so we gradually increase the limit. Now we are having up to 2 depth. Now because we are having up to 2 depth and we want the best quality of DFS. So what we will do? We will apply DFS up to 2 levels. So A, B, then its neighbors. After exploring this limit depth, then we'll go to this side. Okay, so we increase the depth so that we can get some result up to same as BFS, because we didn't find solution at length 1, at depth 1. Now we are trying to find depth 2, then we'll try to find at depth 3. Okay, because we know that the shallowest node is at depth D, that D we are trying to find out. But when we are executing at a particular gradually increased limit, we are using depth first, because we want the property of BFS as well as DFS. So this way we use iterative deepening. Next level. Few nodes are generated multiple times. For example, the root node will be generated every time. Okay? But that is only one node. Its neighbors will be generated multiple times. Those are only B. So root is just one. So we can manage that increase. So to maintain the property of BFS as well as DFS, we are paying a cost of generating many nodes again and again to get the best solution. Okay. it is complete because we are checking each and every node, okay, on a particular depth. It will give us optimal solution because it is trying to imitate the BFS while running the DFS, but it is trying to imitate BFS by putting the gradual increasing depth limit. Okay, space complexity will be order of B into D. It is not now B into M because it is not depth first that we are going to maximum depth. We are gradually increasing the depth, and maximum we will go up to D because there we will find the solution. We will not need to go to D plus 1 depth because before that we will get the solution. And the time complexity will be order of B to the power D because we are only evaluating up to D level. This is our iterative deepening search, IDS. Now the last point, bidirectional search. We have discussed about depth first search and breadth first search. Okay, now what else we can do? We can run the idea of two simultaneous searches, one from backward, one from forward. Okay, so that is bidirectional search. Idea is to run two simultaneous searches, one forward and one backward. So we'll start searching from start node, that is source, and goal also, and we'll meet somewhere in between. So what is benefit of this? Why we are trying to do this? Because if we are taking total D time, if D length is there, total D depth, then one side we will move D by 2, another side will move D by 2. So we will be running very fast, just half of the actual one. And what is challenge here? Challenge here is we know what are successors of a node. We can run bidirectional search only in one case, when we are able to calculate the predecessor also. Okay, so if we are able to search the generate the predecessor, then only we can run the backward search. Otherwise, we need to go for BFS or TFS techniques. This is the idea, that start from start point also and from goal point also. From here move D by D depth downwards, from here move D by 2 path length upward, and then stop at a middle point to find the fast solution. So this is the concept of blind search. So in this particular lecture, we talked about uninformed search techniques, and we discussed the most popular uninformed search techniques, breadth first search and depth first search, with few possible better solutions, like the combination of two, that is iterative deepening and depth first search. And at last we concluded with bidirectional, that if we are able to calculate the parent node also, successor we know, if we are able to go upward also, then we can run bidirectional search to decrease the time complexity to just half. Thank you.